Hi, everyone. Thank you so much for joining today's online seminar. I'd like to say a special thank you to our speaker, Dr. Stef Roux, for joining us today. And before he begins with his interesting seminar on parametric down conversion and its complexities, I'd just like to give a brief introduction. So Dr. Roux has PhDs in both electronic engineering from Pretoria and theoretical particle physics from Toronto. He has been a faculty member at various universities, both in South Africa, including Potchefstroom in Pretoria, and in Canada at Ottawa University. He has also worked at government labs, including the CSIR and NAMISA, as well as in industry with JDS Uniphase. Currently, he is affiliated with the University of KwaZulu-Natal. His interests include various fields in optics and quantum physics, but he has focused on quantum optics and quantum information in the last decade. So we would like to welcome you, and we're looking forward to your talk. Just to let everybody know, there is a slight delay in the slides, but it should change within a few seconds. Thank you so much, Dr. Roux.
Well, thank you very much, first of all, for the opportunity to present this talk to you. So I'm going to talk about parametric down conversion and its complexities. And this analysis is done with the aid of a formalism that I'm presenting in this book on functional phase space methods, in which I describe quantum optics in all its degrees of freedom. Now, what do I mean by all degrees of freedom? Well, the idea is that the formalism would incorporate the spin and spatial temporal degrees of freedom with the particle number degrees of freedom. And the spatial temporal and the particle number degrees of freedom are continuous degrees of freedom. So the example I have here is a ladder operator, or at least the commutator of ladder operators, which produces an identity for the particle number degrees of freedom, the Dirac delta function with these wave vectors for the spatial temporal degrees of freedom, and a Kronecker delta with the spin indices for the spin degrees of freedom. Also then use these ladder operators to define quadrature operators as the sum and difference of the ladder operators. And then they will produce a commutation relation which produces the same result apart from a factor of I. Now, the reason why we're interested in quadrature operators is because their eigenvectors can serve as a basis to incorporate all these degrees of freedom. So we're interested in the eigenvalue equation of this form. The quadrature operators is a function of the wave vector for the spatial temporal degrees of freedom, and it also carries a spin index. Those variables are transferred to the eigenvalue so that it becomes an eigenvalue function. But the eigenvectors do not explicitly depend on these. So you can see there's a truly vast number of eigenvectors because for every eigenvalue function, there is a unique eigenvector. Now, these eigenvectors obey orthogonality conditions, and they are now represented in terms of Dirac delta function nulls, which means that these Q's are functions, they are not just variables. So both for the Q's and the P's, we have orthogonality conditions. To satisfy these completeness conditions, but expressed in terms of functional integrations. So this D is a functional integration measure, and if it's got a little circle, it simply means that every degree of freedom is divided by 2 pi. So in other words, the quadrature eigenvectors represent complete orthogonal bases. Now, they are not states realizable. And in the formalism, when we have the Q's and P's, they are originally represented the eigenvalue functions, but they now become parameter functions for these eigenvectors. And we eventually treat them as field variables for these functional integrations. Together, they can then be considered as the field variables, a functional phase space. Now, because we have a phase space, then we can define Wigner functionals. Now, just to remind you, when I only look at the particle number degrees of freedom, so only one-dimensional, the Wigner functional is defined in terms of the overlap of an operator, like a density operator, by displaced eigenvectors of the quadrature basis. And then there is a Fourier transform with respect to the displacement. So they are displaced in opposite directions on the two sides. When I generalize this to all degrees of freedom, it's a functional integral. So it's a functional Fourier transform. And that tells us that this overlap now incorporates all the degrees of freedom. And the kernel of the Fourier transform is now given by this expression where the x and p represent field variables, and they are contracted with a diamond contraction, which I define in this way. So in other words, it represents an integration over and a summation over shared spins. Now, this diamond contraction is going to show up in this talk over and over again. So that's basically just a quick summary of the formalism. So now we can start to discuss the parametric down conversion process. And for that, we begin with the squeezing operator. So if I include all the degrees of freedom, then we'll incorporate squeezing kernels instead of just squeezing parameters. And these squeezing kernels are now contracted with the ladder operators. And I'm going to convert this now to a Wigner functional, which then has this form, an exponential function, in which the alpha now represents complex field variables, and the taus are kernels that are formed from the squeezing kernel. And so when you see a function with the subscript diamond, this function, all the products are represented by diamond contractions. Now, what we're interested in is to now see what happens when we apply the squeezing process to an arbitrary state. And what we see is that the Wigner function of that state is transformed by a transformation of its field variables that are given in terms of kernels that are again produced from the squeezing kernel in this way. Now, these transformations are Bogleubov transformations, which are given here. So just to review, I can perform a transformation on the ladder operators to produce new ladder operators by making some linear combination of the previous ladder operators, each of which is contracted with a kernel, which we call the Bogleubov kernels. Now, the idea is that the new ladder operators must obey exactly the same commutation relation as the original. So that imposes a condition on the kernels given by these two expressions. So these expressions now define it as the conditions for a Bogleubov transformation. Now, next, all I need to do is to apply the Wigner transform of a ladder operator to show that it produces these complex field variables, which are formed in terms of the quadrature field variables as the real part and the imaginary part. And then we see that we can, in other words, get these Bogleubov transformations on the complex field variables, as shown in the previous slide. So then what we want to do is to apply the squeezing process to a vacuum state. So the Wigner function for the vacuum state is the simple exponential function here. And when we apply a Bogleubov transformation on such a vacuum state, we obtain the squeezed vacuum state with an expression given in terms of this exponential. And in this exponential, we now have kernels A and B complex conjugate. And these kernels are again formed by contractions of the Bogleubov kernels. So now we identify the result of a spontaneous parametric down conversion as a squeezed vacuum state. But in the case where we have stimulated parametric down conversion, then we can also have a seed coming in together with the pump. And then the output will be a Bogleubov transformed version of that initial state. So that was when I consider the down conversion process as a squeezing process. But maybe a more accurate way to consider that is as an evolution process. So in that case, I would like to write down an evolution equation. So we use the von Neumann equation for spatial evolution. So in other words, with respect to some instead of time. And in this case, it looks like this, where I have my temporal derivative. And instead of the Hamiltonian, I have a propagation operator or a momentum operator. Now I convert this to Wigner functionals, and then I get an equation of the state and the Wigner functional of the propagation operator. I would have had products of operators. I now have the star product of these Wigner functionals. Now, the Wigner functional for the propagation operator can be written in terms of a construction process applied to a generating functional. And the generating functional is given by this exponential function. In it, we have field variables for the down-converted fields, the alphas, and also for the pump fields, the betas. And then we have all these other auxiliary field variables generating parameters for the process. The construction operation is now defined in terms of functional derivatives with respect to these auxiliary field variables. And they are contracted on the T vertex, which represents the nonlinear process in the nonlinear medium. So then I end up with this evolution equation here, in which the Wigner function of the state is now combined with the generating functional, with the star product. And these can be evaluated even if we don't know what the Wigner function of the state is. And then we apply the construction process on this combination, and afterwards we set all the auxiliary field variables equal to 0. So when we do that, we get the complete evolution equation for the process. Now, it's a fairly complicated expression. We have 6 terms here, and they all contain the nonlinear vertex kernel for the process, which is contracted on the pump field variable, on the down-converted field variable, and also derivatives of the state's Wigner functional. Now, it's not so easy to solve such a complicated equation, but fortunately, we can introduce a simplification. And that's based on the typical experimental conditions. So we can assume that the pump is a strong coherent state. And then we can write this as a Wigner functional for a coherent state in which this zeta represents the parameter function, and then some unknown Wigner functional for the state. And we can do this because in this scenario, we don't expect the two to become entangled. So therefore, the strong field perturbation theory, the basic assumption is now that the pump, which is a coherent state, on phase space is just a little narrow Gaussian function, and it's shifted very far away from the origin. So we can replace the field variable for the pump with the parameter function of the pump, which is now basically the point where this coherent, function of the coherent state is sitting, plus a new field variable that is defined relative to that point. And that will be relatively small because of the small size of this Gaussian. So we can now make an expansion in terms of this new field variable. And the leading order in this expansion then represents the situation where we just variable with this parameter function. So that corresponds to a semiclassical approximation because this parameter function now behaves like a classical field. And so when we do this semiclassical approximation to that evolution equation, it simplifies quite significantly. And we just get this little equation here with 2 terms, in which we now have this H kernel, which is formed by contracting the pump parameter function on the nonlinear vertex. Now, because this pump parameter function is strong, has a large amplitude, it provides a bosonic enhancement all the sub-leading terms will then contain these t-vertex without such an enhancement, so they are unenhanced, and therefore we can discard them. So we will from now on only use the semi-classical evolution equation. Now we can use that to consider spontaneous parametric down conversion. In this case, we assume that the squeeze vacuum state is the state that we're going to see. So we substitute this as an ansatz into our semi-classical evolution. And that then leads to these differential equations for the kernels, the A and B kernels, and they're contracted with that H kernel that we've defined. Now, to solve these two equations, we just integrate them over Z and then perform repeated back substitutions. And that leads to expansions for the A and B kernels that are given here. For the A kernels, we have the identity, which basically represents the initial state for just a vacuum, and then all the even contractions of these H kernels. For the B kernel, we have all the odd contractions of the H kernels. Now we've got the Z, a Z symmetrization operation, and it comes from the fact that we've got two terms in these equations. So now we more or less have our tools ready. So now we can consider some applications. The first one is not a very complicated one. We're just going to image the down-converted light. So we illuminate our nonlinear crystal with a pump to produce spontaneous parametric down conversion. And then the down-converted light is sent through a 2F system onto a CCD array, where we image the output in the far field. And for non-collinear phase matching conditions, we're expecting to see a ring. Now, to do the detection on the CCD, use the photon statistics. And in the calculation, we're going to do this with a generating function for the Wigner functionals of the projection operator. So that generating function is given here. It's in a Gaussian form, because since we're going to do functional integrations, we need to have everything in Gaussian form. So that is very convenient. In here, we've got this D represents the detector kernel. So we can model an arbitrary detector with that kernel. And then the J represents generating parameter. Now, what we are really interested in is data. We can obtain that from this generating function after we have performed the integration of the Wigner function of the state and this generating functional. We apply one derivative with respect to the generating parameter, and then we set that generating parameter equal to 1. That produces the average photon number. So now we perform that calculation, and what we get then is the trace of A minus the identity contracted on the detector kernel. And if we detect the kernel is a single mode detector, it just becomes the overlap of that kernel by the detector modes. And we can perform the calculation of that to all orders. We get some summation expression here. And we can also then evaluate the summations to get the closed form expression here. Now, in these expressions, you get this capital C parameter, which is a squeezing parameter in terms of the experimental parameters. We also have this rho, and the rho contains the output coordinates. I've plotted this output here. So there's also the R0 that represents the radius of the, and the capital R represents the thickness of the ring. Now, this plot is done in the weak squeezing limit. So in other words, although this function is shown here when the squeeze parameter is larger than rho, in the weak squeezing limit, we would have the opposite condition. What that would mean is that rho and C would change places, and the CHI, which is the integrated hyperbolic cosine function, would become an integrated cosine function, which is just CI. So this is what to look at as a second example, the second order correlation function. So for that, we use this setup here. It is a little bit different. After the pump illuminated the crystal, we identified two particular beams, namely the signal beam and the idler beam. And then the 2F system imaged that onto two detectors that lie on opposite side of that ring. The outputs of these detectors are typically sent to a coincidence counter to now record the correlations. So in this case, our calculation involves as a twin beam state, so it contains two field variables for the two respective beams, the signal and the idler beam. And each of these is now multiplied with a generating function that represents the particular detector, either the signal detector or the idler detector. And they also have different generating parameters. So after we evaluate the function integral over both of these, we take derivatives with respect to each of these generating parameters and then set them equal to 1. The result then produce these two terms plus some other terms that are small and that I've discarded. In the first term, you recognize that we again get this distribution, which is this A minus the identity contracted with the detector. But we get that both for the signal detector and for the idler detector. In addition, we get another term with the B kernels, which now connect these two detectors. So this last term represented true correlation. And the first term represents the accidental correlation. Now, we would like the true correlations to dominate, and we can do that by playing with the squeezing parameter. The A kernel, if I subtract 1, what is left is to leading order, second order in the squeezing parameter. So this whole first term is fourth order in the squeezing parameter. The second term, the B, at leading order is linear in the squeezing parameter. So this term is just second order in the squeezing parameter. So if I make the squeezing parameter small, the second term will dominate. So therefore, we work in the weak squeezing limit. So here we just need to calculate this overlap of the B kernel by the detector modes, where I again, when I calculate that, I get this expression, it is product of these two functions, the exponential function and the sin squared function. In the argument of the exponential function, I find that I'm dealing with the sum of the locations of the two detectors. And in the sin function, in the argument, I have the difference of the locations of the two detectors. Now, to understand how this works, let's first look at the sin function. So I'm going to fix the location of the signal detector and put this at some point. And then the sin function will produce this ring in blue. And it has a radius of twice R0. Now, the other function, which is this exponential function, basically becomes a little Gaussian. And the width of this Gaussian is given by this WC, which is inversely proportional to the width of the original pump. So normally that's relatively large. So the WC is small. So it's a very tiny little Gaussian function. And it must overlap with the ring. Now, if you look at what is in the argument, that means that the two locations of the two detectors must be roughly equal magnitude, but opposite in direction. So that's why we get them pointing in opposite directions, and with the one lying on top of the ring. And now, if we move around the locations of the detectors, all the points where we will get non-zero results would lie on this ring with the dashed lines, and that exactly coincides with the same ring that we got for the photon distribution. So now we can move on to stimulated parametric down conversion. Now, in stimulated parametric down conversion, the idea is to have a seed beam that comes in together with the pump, and provided it matched the phase matching conditions, the seed beam will then become a signal beam on the other side. And then we will also get an idler beam. The signal beam we can call the the parametric amplified beam, and the idler beam is the difference frequency beam. Now, as we mentioned, the output state is expected to be a Bogoliubov transformed version of the seed state. So, in other words, we apply a Bogoliubov transformation to the Wigner function of the input state. We substitute the classical evolution equation, and again we get differential equations, but this time now for these Bogoliubov kernels. We can again solve them by integrating over Z and back substituting. The result looks similar to what we had for the A and B scenario. The U kernel has the identity plus all the even contractions, and the V represents all the odd numbers of contractions. But there are some differences. Because of this half, and because we only have one term, we will get factors of a half for every H kernel here. You can see that. And also, we have the Z symmetrizations. But other than that, they're very similar to the A and B kernels, and one can also show that it's consistent with the A and B kernels for the spontaneous case. Now, as an application, we look at the parametric amplified coherent state. So now we pick as our seed just the coherent state. So the Bogoliubov transformation of a coherent state produces a displaced, squeezed vacuum state, even here. And the parameter function that represents the displacement is now an inverse Bogoliubov transformed version of the input coherent state parameter function. The one with the U contraction represents the signal beam. And the other one with the V contracted into the complex conjugate of the parameter function is the difference frequency idler beam. So if I now look at the output distribution, I'm again going to get the same term that I had with the spontaneous parametric down conversion. So you can never get rid of that. But in addition, I now have this other term where this inverse Bogoliubov transform function is contracted with my detector kernel. Now, in the non-colinear, this will separate into two separate terms for the detector in the signal beam and for the detector in the idler beam. Now, there's one thing that I need to point out, and that is that because of this contraction by the Bogoliubov kernels of the original parameter function, it means that I'm not going to get the original parameter function in the general case. If I consider weak squeezing, and I can assume that U just becomes the identity, then yes, in that case, I produce the original beam. But in that case, I don't get any parametric amplification. Of the squeezing parameter, I'm going to get this distortion. Now, this expression here gives an indication of what is happening. So my parameter function is displaced because of non-collinear phase matching conditions. And then it is overlapped with this huge function, this ugly function here. And it represents a ring in the non-collinear case. To see what happens here, we can just consider the original parameter function as this little Gaussian that is shifted off axis for the non-collinear case. And ring. And now you can see the distortion that occurs because of that. As another application, we can consider photon addition. So the idea of photon addition is we assume weak squeezing so that we only get a single photon pair. And then we put a heralding detector in the difference frequency beam or the idler beam. When we detect a photon there, we know that there is a photon added to the signal beam or to the seed to form the signal beam. So it becomes a photon added state. One can, of course, use a fixed input state, multiply that with the generating function for the photon statistics, and take arbitrary numbers of derivatives to add arbitrary numbers of photons. However, we want to do this analysis for an arbitrary input state, and we're only going to consider the addition of a single photon. So that's why we can go to this weak squeezing limit. In that case, we we can replace our two Bogleubov kernels, the U with the identity plus another kernel, which is second order in the squeezing parameter, and the V is represented by a kernel with a squeezing parameter. Then we substitute that into our seed state to produce the twin beam Bogleubov transformed state. Then we multiply it with the generating function for the statistics measured in just one of the two beams, and we integrate over that beam, but we leave the other field variable so that we can still get the state in the signal beam. Then we take one derivative for a single photon and put the generating parameter to 0. And because it's a non-trace preserving process, we will need to normalize the thing afterwards. So that's going to produce this normalization constant. But now, once we've done this, we can now expand it to second order in the squeezing parameter. And that's going to produce this equation here in terms of function derivatives and contractions on this detector kernel, which is addressed by this V kernel. And that is applied to an arbitrary input Wigner functional. Now we can do the calculation. If we select a coherent state, for instance, and we substitute that into that equation and apply the function derivatives, it produces a little polynomial here, and this is the normalization that we get, which is then multiplied with the Wigner functional of the coherent state. In this case, this M sub V represents the distorted version of the detector mode, which is then also normalized. And here I plot a two-dimensional version of the Wigner function when it is restricted to the plane in which we have this mode. And slice it through so that you can see it becomes negative here. So then as a final application, we consider pump shaping. So the pump is still a coherent state, but its parameter function is now not just a simple Gaussian, it's now a Laguerre Gaussian mode. But we make things a little bit simpler just by putting the radial index to 0. So we just look at the azimuthal index. So then the parameter function is given in terms of this generating function, where this mu represents a generating parameter. This sigma is the sign of the azimuthal parameter, and we want to keep track of this because this can tell us what's. So we put this inside this gamma, and when gamma is contracted on the transverse wave vector, it produces this expression. And when it becomes part of the kernels, the H kernels, we do two transverse wave vectors, and we define this quantity in terms of this kappa plus or kappa minus. And we want to keep track of these because they're going to tell us what the topological charge is. Now the calculation is quite complicated. So just to give you an idea, remember that A is expanded to higher orders. So the mth order term in that expansion will now become the original mth order term where we just had Gaussians times some generating function in terms of m different mu's. We have to take the same number of derivatives with respect to all these generating parameters. So in other words, what we're going to get, for instance, for the A kernel is 1 plus all the higher order terms. And here I write them. The H2 is the original one where we just had a Gaussian. And the P2 is now a product from the generating function. And these polynomials are shown here. So P2 and P4. In this case, for the A, where I pick L equals to 2, I get these expressions, and in all of them, you can see that the kappas come in as the modulus of the kappa. Now, because of that, it means that there is no topological charge. So the A kernel will not have any topological charge coming from the pump. On the other hand, the B kernel, remember, has all the odd number of contractions. Again, the H's represent the original terms in the higher order expansion. are now these polynomials that come from the generating function. In this case, for all the p's, where I pick L equals to 2, I get a kappa plus square. And because it's not a modulus, it now means it has a topological charge of 2. Of course, the terms can also have other factors, but they will all just contain the modulus, so they don't contribute to the topological charge. So that means that the B kernel gets the same topological charge as the original pump. So in this case, it's equal to 2. So now just what we see in this pump shaping example, first of all, we notice that we have all these polynomials for the higher order terms. And that even for p equal to 0 means that these higher orders become more and more distorted when I've got a non-zero azimuthal charge. Now, of course, if I consider the weak squeezing limit, I will only have the leading order terms in these expansions. But the moment I increase the squeezing parameter, then I'm going to see more distortions in the beams. And then as far as the topological charges are concerned, let's look at the stimulated case, the non-collinear down conversion. Then we get the U and V kernels, and they will behave the same as the A and B kernels. So then in the signal beam, which is for the U kernel, which is the parametric amplified kernel, we don't get a topological charge coming from the pump, but we do get topological charge if the seed beam had a topological charge. In the idler beam, remember, we have the same topological charge that comes from the pump, but it is contracted with the complex conjugate of the seed beam. So therefore, we get the negative topological charge of the seed. So in other words, in the idler beam or the difference frequency beam, we get the topological charge of the pump minus that of the seed. So that is the full story. Now I'm just going to summarize. First, I told you about the basic formalism. It is based on the quadrature basis to include all the degrees of freedom, and that led to a functional phase space formalism with Wigner functionals. So then we did the squeezing process of transformation of the Wigner functionals. We also derived a semiclassical evolution equation for the down conversion process. The initial evolution equation was quite complicated, but thanks to the semiclassical approximation, we could simplify it. For spontaneous parametric down conversion, we select the squeezed vacuum state as the input state, and then we could solve the kernels for the squeezed vacuum state. And as applications, we consider the down converted photon distribution. And we also looked at the second order correlation functions. In we showed that we have this Bogleroff transformed initial state that we can solve the Bogleroff kernels for. And then as application, we had the parametric amplified coherent state. And then I also showed you how you get these modal transformations, which can lead to distortions. As a second application, we considered the photon addition, and we could then calculate the output photon output Wigner function for that state. And finally, then we looked at pump shaping using these helical modes, and we discussed how that means and how the topological charge is distributed among them. Thank you.
Thank you so much, Dr. Roux. Are there any questions? You're more than welcome to type in the Isaac. Go ahead.
Hi, can you hear me?
Yes, we can.
Yes, I hear you.
Great. Hi, Steph. Thanks for the nice talk. So I wanted to ask, I mean, with this new formalism, like, what more do we learn about SPDC and these linear processes that we couldn't from the previous formalism?
So the basic idea is to increase degrees of freedom. So there's very big literature on parametric down conversion. But what this new formalism provides you is the fact that you can model everything now. Previous formalisms usually make some simplifying assumption, and that those simplifications are often imposed by the formalism themselves. So you cannot in general analyze everything in the same detail that you can do now with this formalism. Does that answer your question?
Yeah.
Thank you, Isaac. Are there any other questions?
Hello.
Yes.
Hi, Stef. Good to hear you speak about this again. Thanks for the talk. I just want to ask you about the last thing you showed about the effects of the topological charge of the when you have the parametric amplification. Is that also assuming weak squeezing? And what will change if you have strong squeezing?
So okay, let me just see if I can understand what you do. You mean the the difference frequency beam or the signal beam specifically, or do you mean
no, either one? Either one. Like you in the first point you show that it will be complicated beam profiles for strong squeezing. Do you see a similar effect if you have stimulated processing?
Yes. So in stimulated, if you've got a weak squeezing, you only get the leading orders. Now, the leading orders are not so severely distorted. And that doesn't matter whether it's spontaneous or stimulated. You will get similar results. It's just that, you get either the A and B kernels or you get the U and V kernels. But they are all based on contractions of that same H kernel. And the H kernel contains the parameter function. And so the parameter function, if it's now produced by these helical modes, that's going to produce those distortions. And so higher and higher and higher orders are going to have more and more and more distortion as you go as the higher orders become more important in the strong squeezing case.
Okay, thank you.
Okay.
Thank you. Is there any other questions? Thank you so much, Stef. There don't seem to be any other questions, but I'm wondering if there's any way for people to contact you if they'd like to discuss it further.
Yeah, they're more than welcome. They can email me. I don't think I have a quick way to show you.
Are you happy for me to put your email in the chat?
Yes, you can do that. Okay.
Okay, great. I did see that somebody was typing a message. I don't know if it was Tatiana.
Okay.
Would you like to ask a question? Okay, they seem to have stopped typing. I'm sure if they... Oh, she's typing again. Okay, she's just saying thank you so much for the talk. So I will just quickly put your email in the chat. And then the talk was also recorded if anybody needs to go and clarify anything. Thank you so much, everybody, for attending.
Thank you.
Thank you so much, Stef.
Yeah, thank you. Thanks for the opportunity.